So let's look over at the all course content and we'll have a quick overview of everything that we've basically covered since the very last exam, right? So basically our exam was not actually that long ago, about 1 month ago, right? So what we basically covered on that exam was only up to and including the PLL. So that means we do have a fair amount of pretty challenging content that we've done since then. Um, this exam, it's going to be pretty hard to wing. Like, we'll cover a fair amount of material tonight on the kind of details, but there's some pretty tricky mathematics. There's going to be like some calculus and some integrals. So to prepare for it, it's not enough to just kind of like passively watch the review tonight and go to the exam. You'll probably want to do some practice on your own, some practice problems. So if you'd have done assignments 5 and 6, it's probably a pretty good start, right? But beyond that, let's just go through kind of what happened. So up until now in the course, we were just doing radio modulation. So we ended off with this PLL, just a method of FM demodulation. The course since that really changes gears quite a lot, right? So the lecture that's usually skipped, really most of these are, we've covered quite a lot of basic probabilities. So that's going to be just Bayes' law, conditional probabilities. The, those end up not being too important most of the time for this course, but they can be involved in it. If you take 428 next term, that's what the entire course is about, right? But yeah, this next one, it's a pretty big deal. It's random variables, right? Random variables and random processes are kind of the main focus of this second half of the course. What we've been working towards are these lectures that we've basically just finished recently in the last week or so, and it is these SNR lectures here. So what we worked up to was a derivation to find the signal to noise ratio of all of the different modulations that we've used. So remember we used amplitude modulation in quite a few different forms, right? We used the dual sideband full carrier, the AM. We used DSB with the suppressed carrier, and we used the both types of single sideband, right? So all of those have their own SNRs, and um, basically the FM radio also has its SNR, right? So to do that derivation, it's quite a lot of work that we've gone through, right? We started off talking about just random variables and processes in general, right? We talked about autocorrelation and cross correlation mathematically. That was pretty useful because then in this next lecture, the lecture 20, we talked about how we can actually know the power spectral density of random signals, right? It's pretty weird that we have a random signal going into like a system, and we still actually know what it looks like in frequency domain, even though we have no idea what it looks like in time domain, right? So that's pretty core for dealing with noise later. Linear time invariant stuff, that's just the same, what is it, 380, right? That kind of stuff. Um, then we start talking about random processes. It's just a family parameterized of random variables. So that's what noise is. It's just a random variable. That's a different random variable whenever we sample it, right? We talked about filtering the noise, more power, spectral density, and whatnot. And then, yeah, basically the SNR is what we worked up to, right? So that's the general overview for what we've covered since the course. So I think tonight what we'll do is we'll cover this exam from 2023. It doesn't look super close to what I expect this year's will be, but it might be fairly close, right? And then maybe we'll cover a little bit more specific details of the SNR stuff, right? So yeah, before that, are there any questions? All right, cool. So I think to really start off here, let's first just quickly look at these SNR slides. So the real key with these SNR slides, right? This is noise and analog communication systems. What we want is just equations at the end. Jake, just to clarify, we only go to the lecture for SNR2, correct? Yeah, except today he covered this tutorial as well. Let me just quickly look if he posted it or not. Um, it would be here, but we did tutorial 6, this one, today in class. So I think that will probably be covered as well, but it's basically just practice of the concepts that we had covered up to the SNR2 slide deck. Yeah. Okay. Okay, cool, cool. No worry. Um, Okay, cool. So, what I want to look for in this SNR1 slide deck is basically just the formulas, right? So, what we have is, like it says here, we have various SNRs in a system. So we have to just know the definitions of all of these, right? So we have the reference SNR, post-detection, pre-detection, and the figure of merit. Once you know some of these, usually the rest are pretty straightforward. The main issue, though, is that a lot of these equations, they're different depending on which modulation scheme we're going to be using, right? So basically, that's the main thing. All of these slides are kind of going through the derivation. The main thing you really need to worry about for the exam, though, is just going to be the actual formula in the end, right? So here is the reference SNR, right? So reference SNR for all these modulations is one of the things that you'll always need to have on your formula sheet, right? So that's basically going to be the signal to noise ratio before any sort of demodulation happens, right? So think about like an AM signal. We've modulated some kind of audio wave, right? And now we have a big strong RF wave, right? It's the power of that RF wave that we're considering our signal here, and we're just considering it in relation to its noise, right? So that's the PS. It has nothing to do with the actual power of our message signal. Remember, when we first started this course at the start of the term, we were talking about amplitude modulation, and a huge part of amplitude modulation was the power efficiency equations, right? Because we had our carrier wave, which basically was kind of wasted power, but it's still part of the signal as far as this reference SNR is concerned. So just remember that one of these main things you need to know for this exam is reference SNR, right? And the reference SNR is just going to be the raw signal to noise ratio of the modulated signal, like the RF signal, right? And then that's also how we get our figure of merit, right? So we have some kind of an radio frequency signal going into our radio, and it has some kind of a SNR. It's the signal power of the RF signal divided by the noise density of the noise times the bandwidth of the noise, basically. That's going to be our reference SNR. We compare that to our post-detection SNR to get the figure of merit. So that's actually going to be basically the ratio of our demodulated message signal power to our demodulated noise signal power, right? So that's the harder thing to find, of course. That's what all of these slides are kind of talking about. But mostly you're not it's not super likely you'll be responsible for lots of the derivation. You might have to struggle with a bit, but it's the equations that really matter. So here, I think in these slides here, he's talking about the SNR equations for the dual sideband with suppressed carrier. So if you remember, we're dealing with the super heterodyne system. So we have our RF signal coming in at some sort of frequency, right? First, we kind of pre-filter it to get rid of its image, and then we mix it by a local oscillator to move the RF signal. Let me just grab an annotation here. So yeah, we have this RF signal coming in at some RF frequency. And then we're going to mix it with super heterodyne, if you remember. We basically are going to be subtracting the frequency of this local oscillator from the RF signal. So now we're going to be at this intermediate frequency, right? This will probably be just some fixed frequency that's convenient for us to demodulate to, right? And then some filtering. Usually when we mix, we get two signals, two copies of the signals, and we're only interested in one, so we almost always have to mix. And then this here is a coherent demodulation that's used for DSP. And then again, we just have to get rid of the high frequency product. So after this whole radio system is kind of like laid out, what Daniel was doing in class is just um, kind of mm, writing down the mathematical expression for the signal and the noise as it goes through here. And in the end, what we really want is this recovered message signal power divided by the recovered noise power, right? So yeah, it is pretty involved, but in the end, it's a fairly simple equation. You just still need to know what it's about. So see, prior to detection, we get this ratio of the signal power to the noise power. So I think this is right where we're still modulated, right? Um, so this would also be the reference, I think. And then down here, we get the other equations here. So here's the summary, right? We have our pre-detection, SNR, post-detection, SNR, and our figure of merit, right? And then, of course, the reference SNR. So basically, this is what the second half of the course is kind of all about, right? It's a lot of work to actually get to the point where we have these simple equations, but now that we have them, it's just important that you use them. So make sure that you write them down on a formula sheet that's convenient. Remember, we have quite a few of them. I think we have four just for AM, and then we'll have another set for FM. So make sure you have them in a nice little summary table. So when you're writing the exam, you don't actually have to go through all these slides, right? Because this is like slide 14 out of 15 on this one, right? There's lots and lots of slides. So yeah, just make sure you have all these equations written down. So then, oh yeah, so it's just talking a little bit more about the reference SNR, whatnot. Are there any questions about that? So that's the basics for this dual sideband suppressed carrier and all of the SNR things as a whole, right? All right, cool. Okay, so let's just go over to the second SNR slide here so we can quickly go through it. Let's do SNR2 right here. All right, so the last slides were about the SNR when we were using dual sideband amplitude modulation with coherent detection, right? So this part is going to be using the easier kind of amplitude modulation. That's with just the one plus here. Remember, it's very easy to modulate this. We just use the envelope detector. And remember, the power efficiency of this equation um, it's not 100% because it has like a carrier from this one term. The power or the SNR analysis of this kind of circuit, it's a bit more annoying because this envelope detector, it is nonlinear. So it's a little bit more of a process to actually get the derivation. But just like the DSB case, right, it really just comes down to the formulas, right? So we end up with a pre-detection SNR equation here. It's very similar to what we were seeing for the DSB case, but just keep in mind all of these little factors, the two here, right? And here we have a Ka factor. There's quite a few little factors often that are different in all of these equations. So make sure you don't confuse them when you're using the different ones. So what we end up with is, okay, so then we go on to SSB, the single sideband. And I just want to see if there's a slide that summarizes them all. That's for SSB and that's for FM. Okay, no. So we'll just have to go to each of the summaries. Okay. Okay, so yeah, basically we have our post detection SNR for our ordinary AM, our dual sideband with full carrier right here, right? Our reference SNR, which is just our signal power in the RF divided by the noise in that bandwidth, right? And then our figure of merit. So in the previous case with DSB, we saw that our figure of merit when we divided our post-detection SNR by our reference SNR. It equaled one, right? I mean, it makes sense, but it's also a bit of a coincidence, right? The ratio of the power in our message signal to the noise in our message signal after demodulating was the same as the ratio to or of the power in the RF signal to the noise in the RF signal. That's not always the case though, right? So we saw with AM with this envelope detector. In fact, our post-detection SNR is worse, right? And that's remember because our reference SNR is just all of our signal power in the RF and the radio frequency divided by the noise power. So we have all that carrier power there, but the carrier doesn't contribute to our message at all. So it almost makes us look like we have a better SNR than we do because a huge part of our signal power is just wasted, right? So that's why the figure of merit for this kind of AM with the envelope detector, it's going to be less than one, right? All right. Are there any questions about AM SNR stuff? Uh, we'll go on to single sideband after this. But yeah, just make sure you go through these slides and you have all of these equations down on your formula sheets because I mean it was several weeks of class, right? It's a lot of mathematical work, but in the end, these questions are pretty straightforward. It's just find the SNR. So you just you identify what kind of radio it is, and you just use the right equation, right? It's not that tricky. Hmm. All right. So yeah, we'll just go on to the single sideband quickly then. So remember with single sideband, we're not like we have half the bandwidth in our radio frequency as we have with double sideband, right? But is it really going to make a difference in the SNR? It depends. Sometimes it does, but not really. So for our single sideband, remember we have to go through the Hilbert modulator. So of course, all this mathematics ends up quite a lot more complicated than just the DSB case. But it is straightforward. It's really just laborious. We did spend quite a while in the last month going through it, so we can't really go through again tonight. But in the end, again, we just boil down to the four equations that we need, right? Our pre-detection SNR, post-detection SNR, reference SNR, and figure of merit, right? So after all the derivation, we get this single sideband pre-detection is just here. Notice again the factors, right? We don't have a AC squared over 2 here, but we do have a 4 here instead of a 2. So keep in mind that's the main difference between the SNRs for all of these AM modulations is these small factors. So just try to make sure you get it right, right? So yeah, post-detection SNR after that, and then our figure of merit just like this, right? So we actually see that our figure of merit for the single sideband is exactly the same as for double sideband. In both cases, they don't waste any power, and in both cases, their SNR in the message domain, like the signal power divided by the noise in the message power, it will be the same as the signal power in the radio frequency divided by the noise power on the radio frequency, right? Let me see. Okay, so Keynes. What is the difference between pre-detection SNR and reference SNR? All right, so that is basically the point in the radio diagram in which we're actually taking the comparing the signal noise power. Okay, so let's see a simple case somewhere here if it's marked. I think we might need to open up the previous slides. Do I have this? Yeah, Clem, this is recorded. You can watch it after I post it. Yeah. All right. So here is basically where we're looking. All right, so the pre-detection SNR, you can see right here, it is the signal to noise ratio. You see after the bandpass filter, right? So it's before we've demodulated it, but it is after we've what is it? We've mixed it and put it through the bandpass filter. So basically, we've kind of trimmed the amount of noise as the noise bandwidth having the same or the noise having the same bandwidth as the signal bandwidth, right? So yeah, at this point in the block diagram, this is the pre-detection SNR, right? Let's see. The reference SNR is usually going to be the same as that, I think. Is it only in the FM case that it's different? Uh, let's just see where it was. So the reference SNR is the same for each modulation scheme. Yeah, I think it's the same. Like pre-detection, it might be different for FM. We'll just have to see when we get to it here. Okay. All right, so here's the SNR2 we were at. So yeah, here is our post-detection SNR figure of merit for AM. We just went through this. And then, yeah, we just did our SSB as well. So again, here is all of our important kind of information here, right? For a single sideband, right? Reference SNR, which is in this case, yeah, it's the same as the post-detection, right? And the same as the pre-detection, in fact. So this is everything for the for AM, right? So it's pretty straightforward. The noise analysis for FM is a bit trickier. Um, Most years he doesn't hold the class responsible for the derivation, but sometimes he does. It's just it involves a little bit of calculus, which is a bit tricky. But you see, he actually puts the equations just on the very top side, or the very first slide, right? So for FM here, just make sure that you have all of the different factors very straight, right? So you see we have BT here. I think that is the actual bandwidth of the modulated signal, right? It's not the bandwidth of the message, right? So for actually doing the SNR analysis in FM, you do have to do a few extra steps, right? In AM, it's always straightforward what the bandwidth of the radio frequency will be. If it's a DSB or an AM, then the bandwidth of the radio frequency signal is just going to be twice the bandwidth of the message signal, right? If it's single sideband, it'll just be equal to the bandwidth of the message signal. With FM, there's no clear relationship, right? It depends on how much frequency deviation that we're adding. So we can use Carson's rule to kind of estimate it. But the concept of the bandwidth in radio frequency domain and the bandwidth in message signal domain, it's not necessarily like one to one, right? So make sure you keep track which bandwidth you're dealing with when you're doing these SNR things, right? So, yeah, for FM, we just have all these equations, right? Pre-detection, post-detection, right? We found this in, I think, 2 weeks ago, or maybe just a week ago, we went through, and there's just a bit of an integral with it. It's not too hard, though. And then we just got our figure of merit from the ratio at the end, right? So that is basically everything, right? The real key here, though, do you see we have W, and that's the bandwidth of the message, right? So our figure of merit in the end, it ends up being um, a function of the message bandwidth as well as this KF, and that's our frequency deviation, right? So we can tune our figure of merit with FM, and we can't do that really with AM, except with the ordinary AM kind, with the envelope detector. We can um we can just tune how bad it is. With FM, we can tune how good it is though, right? So yeah, it's actually very straightforward. We spent a lot of time on this stuff, but it boils down to just all these equations, right? So is that 16 equations? Just four equations for each of the different modulation things, right? Are there any questions about SNR? All right. Oh, why is there no reference SNR for FM? There is. It was right here. Let me see. It was in the derivation here. Um, yeah, here's oh no, sorry, that's for SSB. Um, wait, is it just the pre-detection? Let's see, is that ratio the same? I'm not sure. Let's actually have a quick look over because we went through the SNR of FM. So here, there's this slide deck. I don't know if it's quite worth for you guys to review tomorrow because it's usually not covered and it's pretty in depth, but it does contain the entire derivation of what we had for our FMSNR, it's a bit tricky, right? Because our noise ends up becoming this Rayleigh distributed noise, right? But it's not too bad. It's interesting if for some reason you have spare time while studying here. But in the end here, let us see quickly where he does the final ratio here. So here's the post detection. Did he not manage to finish it? So here's the expected value of the noise. Hmm. I don't know if he had the reference SNR, but in any case, the reference SNR is the same um, for every single modulation. So for FM, it'll just be the AC squared over 2 because the amplitude of FM doesn't actually change, and the reference SNR is literally just the SNR of the radio wave going in there. So it'll just be AC squared over 2. Okay, cool. So yeah, I think that's FM. So if there are SNR questions on the exam, please nobody leave them blank. At the very least, just try to guess what radio it is, right? There's not many types. There's only four kinds of radio, so you have a good chance of being correct. And then write down the correct formulas for that kind, and you'll probably be okay, right? Okay, cool. So yeah, I guess there were no questions about that. Let's have a quick look at the exam from 2 years ago. All right, so the first question, let's see what this is all about. All right. It is a little bit tricky. So this is kind of this is the kind of question Daniel likes to put on exam 2 because remember, exam 2 is supposed to just focus on content from the second half of the course, but all of that content is built on content from the first half. So a big radio design question like this is exactly the kind of thing that you might expect on the exam, right? So this one is quite it's a bit of a puzzle, but it's very straightforward if you've been following the class or a little bit. It really throws you off if you haven't. And in fact, quite a few students got this wrong. Well, almost all of them actually when they wrote this exam. But okay, so consider a message signal whose power spectral density is significant in the frequency band from 100 hertz to 300 hertz, right? So we could basically say the message signal has a bandwidth of 3K, right? You could say like 2.9K, but nah, we can just say it's a low pass at 3K, right? And it says negligible at frequencies below 100 or above. So the radio channel band is available from 1 megahertz up to 1 megahertz plus 3K, right? There's a strict requirement that the modulated signal cannot have significant power outside the above available channel, right? So basically, we have this little RF slot, and we have a message signal that we need to fit into there, right? So the very first part of this is just kind of logical. So we need to, in part A, it says, think of a candidate modulator that meets the requirement, right? Provide a diagram of the block module that has M as the message signal and denote the output. Um, and then it's just asking about the block diagram and everything and the filters. So it's saying we actually need to design this radio now, right? So remember in this course, we've covered four kinds of radio. Yeah, four kinds of radio, I suppose. Um, the three kinds of AM as well as FM radio. So there's really only four possible radios we could build here. So which radio we need to build is, of course, like part of the question here, right? So all we're told to go on here is the bandwidth of the slot available to us as well as the bandwidth of our message signal, and it needs to fit in. So let's just look at what we have, right? 3 kilohertz bandwidth and 3 kilohertz bandwidth. So basically, we need to use a radio that the RF signal is the same bandwidth as our message signal, right? There's only one kind of radio that does that. So we learned AM, and when we use an ordinary AM with full carrier, our RF signal has twice the bandwidth of our message signal. When we use single sideband, it has the same. When we use double sideband, it has double bandwidth. When we use FM, it has at least double. Remember, narrowband FM, when we're barely deviating the frequency, even that has double the bandwidth of our message signal. And then as we add more and more deviation, frequency deviation to our FM, our bandwidth gets even larger. So um, when it's asking us to design a radio that has the same RF bandwidth as message bandwidth, we have to use a single sideband radio, right? So that's the kind of question we end up on here. So this part A here, basically all you need to do is draw the block diagram of a single sideband radio, right? You need to, of course, specify the frequencies of the oscillators, the amplitudes, and the frequency, the cutoff frequencies of the filters. But realistically, that's super quick, right? So if you're kind of quick on this kind of stuff, you can just read this question, know exactly what kind of radio you want, and then you would just draw it, right? So for me, I'll just draw it right on top of the question for now. So basically, we'll have our message signal coming in, right? This will go into this guy here. We'll multiply this by our LO here, right? But since this is single sideband, remember we also need to have we need to use IQ modulation. We need to do the Hilbert transform of our message signal here. And then we need to feed that into a sine wave, right? So our cos comes in, gets shifted by 90 degrees and becomes a sine, right? The Hilbert transform of our message signal comes out. And then at the end, these two things, our message signal modulated by the cos and our Hilbert transform of the message signal modulated by the sine, we add them together and that's what we get, right? The only thing here is that we do need to label the amplitudes. So this here will have a very specific frequency, and that's just going to be given by the center frequency we want. So we want it to be we're moving from 100 hertz to 3000 hertz all the way up to between 1 megahertz and 1.003 megahertz, right? So this can just have a 1 megahertz frequency, right? And then remember, we do need filtering here because these things will cause signals up around like 2 megahertz or, well, we end up at the plus and the minus, and we only want the one, right? So we basically need to have our bandpass filters here and here. All right, so basically that's it. So yeah, you would just draw that and that's perfect. So let's just go over and look at the solutions. It's a lot neater than what I just drew, right? But you see, it's the same thing. So it's just saying that since our signal is 3K, we have to use a single sideband, right? And then I've just drawn the the thing here, but here we need to, yeah, we need to use this one here, the product modulator, right? So phase shifter, Hilbert transform everywhere. Petrina, what symbol are you using for the one multiplied by the Hilbert? Oh, I was just using an H there, right? But it can be anything. If it's kind of frequency limited, it'll just be a 90-degree phase shift, so you can just use a phase shifter. But for us, it's always going to be that awkward convolution, right? All right, so that's the main thing. This whole question is really just about that basically, just drawing the filters, drawing this product modulator, right? Are there any questions about that part one? So it's just a design question, giving us some constraints and asking us to design a radio that fits them, right? All right, cool. So part B, it says for the modulator of your choice in part A, provide a diagram of the receiver block. And then denote by D the output of the receiver block. We desire high post detection SNR. In order to minimize the cost, try to make it as simple as you can. If your choice of modulator demodulator requires frequency or phase synchronization, assume the synchronization is achieved by another modulator. So it's saying if we're using coherent detection, you can just take it as a given that like you have in phase signals you can use, right? So yeah, remember in this course, we've studied quite a few different demodulators, right? That's basically what we're doing here. We're designing a receiver of some sort, right? So there are quite a few different ones for AM. We've learned our coherent demodulation that we use for DSB and single sideband. Sometimes we need to use a Costas loop for that to make it coherent, but it said here in the question that we can assume that phase synchronization is just given. So we don't really need it. It's just multiplying the RF signal by exactly the same carrier that it was modulated with. That's the idea, right? But we also learned some other demodulators. We learned envelope detector that we can use for the one type of AM, right? That's just the diode and the RC circuit you did in your lab. And then we learned about all the FM demodulation techniques. So yeah, for the part two, it's really just choosing the demodulator that matches the modulator that you picked in part A. So if you are doing this on the exam, just make sure it's the same one. Um, a lot of students, they used the wrong modulator in part A of this exam, and then they used the wrong modulator again, but not even match it in the part A modulator in part B. So they got quite low marks for that, right? Just even if you're wrong in part A, make sure you're only wrong, like make sure your part B is the same kind of wrong as you were in part A, right? So if you said FM in part A, make sure you do a FM demodulator in part B, right? So yeah, as far as this question goes, we chose SSB, so we need a coherent demodulator. We just multiply our incoming signal by our exact cosine, basically, of the input, and then we low pass filter it. So we can just look over at our solutions and, right, it's a very, very simple structure. So the real key here is it's been told to us that this phi is perfectly locked in and it's just done for us. In the real world, we need some sort of a PLL or a pilot signal or something to deal with, right? But no, it's been a bit easier for this. Okay, so that's part B, right? So it's just drawing the diagram and specifications for the demodulator. For part C, it gets a little bit more mathematical, I suppose. So assume that white noise has this power spectral density and not over 2, and denote by PM the average power of the message signal. Okay. Express the post-detection SNR of your chosen design in terms of the notation defined above and the notations you define if necessary, right? So now all we need to do is find the SNR of the radio we designed, right? So what do? We just look up the formula in our formula sheet, right? So at the start of this review session, I just went through the SNR slides, right? We had 16 different formulas, and 4 of those were for post-detection SNR. So we chose single sideband. So yeah, we just really do just that. We do post-detection SNR for single sideband here, just the formula. You just need to copy down and then match it up with what we've done so far in this question. It's been told to us that we have the message signal's PM, and the noise density is this, so we just need to match it up, right? So when we look over here at the solutions, we just literally copy down from the sheet exactly what we have, right? PM for and not everything, right? So that's it, right? A huge amount of this course is just knowing when to use what radio, right? So nothing has as narrow bandwidth as single sideband, and nothing has as low of post detection SNR as super high distortion FM, right? So yeah, it's a huge part of this course is just knowing what modulation to use when. After that, it's super easy, right? So this question, you just draw two block diagrams and you copy down one formula from your formula sheet, and that's full marks, right? So yeah, hopefully this exam will be similar, right? Are there any questions about that? So that's the entirety of question one on this review exam. All right, cool. Let's have a look then. Problem two. Okay, there's a lot of these conceptual problems. It's sort of like the questions that Daniel asks in class, right? When he's just like kind of I don't know. He asks like a basic question, and then the class is kind of stumped, right? He tends to ask those on the exams as well, right? So here, it's really just about the meaning of words, right? This would be annoying if you haven't been coming to class because like words don't really have meaning to you, and it's hard to go through the notes quickly enough to really figure out what all of the words in the sentence mean, right? But that's kind of what it's about. So just try to have, if you can, in your cheat sheet, like a little glossary of defined words, right? So here it is saying, suppose that a baseband real value deterministic voltage signal, M of T is band limited in band from negative 4K to positive 4K. Does this mean this signal has finite energy in the infinite time horizon? If yes, argue why it is true. If not, provide a signal that has infinite energy and still band limited as specified, right? So yeah, this is it's a little bit of a puzzle, right? And it is worth like 10% of the final exam. So it's not trivial. Of course, it's pretty easy if you know the meaning of all these words, whereas it would be a lot of work for 10 points if you don't. So it's like it's saying baseband. So what does baseband mean? It just means there's no carrier, right? It's kind of not been modulated, right? It's just our raw message signal. It's real valued, so that means it has conjugate symmetry in the frequency domain. We don't know if we need to know that yet or not, but we might. Deterministic. It might not even matter, right? Even if it was a random signal, we might still know quite a lot about the signal, right? And then it's saying if it's a voltage signal, that might be important. And then the real key here, it's saying it's band limited, right? So almost none of this stuff that he's mentioned matters, apart from the fact that it's band limited, right? So he's saying that the spectral content of the signal is limited to a very narrow frequency band, right? From the very first class, and he's mentioned it a few times, it's just the analog of Heisenberg's uncertainty principle. It's not even an analog, it's the same thing, really. If a signal is limited in frequency,